Hello guys, welcome back to our day 8 lecture of our deep learning playlist. So basically, I'm your educator Suresh, and today we'll be covering regularization techniques. So if I just show you what we have covered till now. So in the last lecture we already covered loss functions and optimization techniques. So we divided it into lecture parts to cover loss functions and optimization techniques separately. So we already covered the mean square error, loss function, and MA. We already covered these loss functions. Some of the loss functions we will be covering when we encounter them in our journey of deep learning. And we already covered optimizers, different types of optimizers. We have looked on to momentum, SED, and the lag. We also had looked to have already looked to Adam optimizer of RMS prop. We already used different visualization tools, which is already given to you. So basically, in our next lecture, so we already have a plan. Like we'll be doing. This plan may actually change, but this is the whole idea of the plan. Like we'll be covering regularization technique and then hyperparameter tuning and then hands-on neural network. So this will be a hands-on neural network will be a big lecture basically in which we'll be covering how to make a neural network, basically in model building and then applying different the loss functions we'll be looking at. Earlier part we have already seen. So this is basically this will be going to be a very big lecture. And before that, we will be covering regularization technique, which is our today's lecture, and then hyperparameter tuning. So I thought that I just we should just cover theoretical aspects of regularization techniques and hyperparameter tuning, and then finally, when we will be learning hands-on neural network, then I will basically show the intuition of them here only because it will be unnecessary to show these things two times. So basically, in hands-on neural network only will be covered the basic both thing applying both thing application of both these lectures here. So basically, in today's and next lecture, I will not be showing you code, but don't worry, we'll be covering that on hands-on neural network. I will be making a complete neural network, and basically we'll be training a neural network and then just trying to see different do hyperparameter tuning and apply different loss function regularization techniques. And then we'll also, then later parts of the lecture, we'll be looking at handling training issues. Normalization, we'll try to cover some basic understanding here only and improving model generation. So basically, this is the plan. So let's just go to today's plan only. So regularization techniques. So we'll be looking at different regularization techniques. And so basically why we apply regularization techniques and why all this thing is done. So what happens is that when a model overfits. So I hope you already know what is overfitting, but let me just show you a diagram which I didn't paste in the wait, wait, overfitting and underfitting in ML. So let's just go and look at these diagram. Yeah. So basically, what happens like if you have a neural network, so this is basically a classification problem, and what is happening is that so basically what is happening that there is model is trying to learn every aspect. So basically, it's not getting the idea, the pattern of our data. It is trying to just learn. So if we just try to I just try to teach you make you understand like in this diagram. So in this diagram you can see like here the model is trying to learn every data points of the training data. It is not trying to understand the hidden pattern behind it. So that's why we can say that model is overfitting. If you look at it is underfitting because model is not trying to learn anything. So we basically have to get a balance between the overfitting and underfitting. So why model overfits? We will be looking at why model overfits, and to avoid the overfitting and underfitting, we basically use regularization techniques. So this is the key reason behind overfitting and underfitting. Don't worry, we'll be looking at looking the code thing in our data lecture. So most of the things will be clear by looking at the uh, code basically the code thing. So I just try to make you understand. I hope you already know the concept of overfitting. If you have come here in deep learning, so you already have a knowledge of data science. So you already have the gist of what is overfitting and what is underfitting. So let's just try to understand, to revise here, and let's just move to a higher topic or to a higher goal. So basically, if I try to explain the same thing, so what is happening that we have a classification or regression problem. So if I just go to any best so this is the best I think I can get here. So if you just try to look at the regression setup, so in regression setup you can see that this is happening because our model is not learning properly. It is just making a linear regression line, and our model is not learning. So we can say that symptoms high training error close to test error, high bias, and then just right. So basically, this is the balanced. So our model is learning the pattern. It is not trying to grasp or just learn the our training data points. It's trying to find the pattern. So training error is slightly lower than test error. So basically, if I just tell you that what happens when how we judge basically that our model is overfitting or underfitting. So basically, where our model test accuracy or test loss is kind of close to a training loss. So that's the same thing written here. Training error slightly lower than test error. So basically, if they are very closer to each other, so we can say that it is a balanced performance. If what happens if that there is a huge difference between like a model is performing too good in training data set, but it is not performing on test data set or validation data set, then we can surely say that our model is overfitting because it is just learning the training data points. It is not finding any hidden pattern behind the training point, the reasoning why the things is happening. It is not able to find it. So the same thing is written here. So in the just right, we can say that training error slightly lower than test error. You can just see and high very low training error much lower than test error and high variance. So basically, in overfitting, the model is just trying to learn all the data points, and that is why the training error is too low because it has already learned all the data points. If you give any training data point, it will just because it has just like it has already learned everything. It knows the data point. It is not finding the pattern. It is not finding the line which best suit for other data set, but only for the same data sets. And that is why the training error is less. But in when you look at the validation error or testing error, it is too high. So that is why we can say that model is overfitting, and same underfitting if high training error and high validation error. And in the balance, you got the idea what is the balance. So there is a approximately same like training error and validation error. Then we can say that our model is fit and our model can predict on the new data set. So this is why what overfitting means. And regularization is basically the steps which we take to avoid overfitting. So if I just try to let's just go. Well, first I should tell you why the in neural networks the overfitting basically takes place. So if I just try to let's just draw it and understand. If I add a blank page, I think I should add a blank page here. Mhm. Did it add a blank page? I didn't add a blank page. Yeah, now it added a blank page. Let's just yeah. So what is happening? Like why overfitting takes place? So the causes of overfitting can be that like uh, causes if I write. So basically, one of the very major cause which should be addressed here is that complex. One second, please. So one of the biggest and the major issue is our complex. neural network. So, why the complex neural network thing happens, and let's just take an image from here and just place it to understand. Uh, so, let's just copy it, copy image. Let's just, if I paste it here, and yeah. So, what is happening? Like in, suppose that if we have, let's just make it by ourselves only, so it will be better to understand. Let's just make a classification setup. So there are two types of data points. So let's just make it. That's simple thing. And then we have cross data points. So what would happen like if we just take a neural network, which is like if the data point is passing from a single neuron, so it will just give you a linear setup line. Like if I just take a different or what should I take? Like if I take. So what is happening? Like if you are having a single neuron for a basically the all data points are passing. Like if you have different data points, input points, and it is passing from a single neuron, which is our basically the neural network model, and then we are getting the result. So if and applying linear activation, so what will happen? Like if we are taking only a single neuron as our neural network model and then passing input data points from here, and you already know there will be like if there are many data points, so basically they all are passing, and then you already know that there will be with some this bias addition, and then the simple if we are applying linear activation function. So basically, what is the output coming? Is the basically the it is basically the uh, output only because there is nothing like another activation functions like relu or sigmod or anything like that. So basically, the output will be the same. So when having a linear activation function, we will get just a linear line of it, like wx plus b. So so you can just say that because of a single neuron as a neural network, you already know there will be weight term plus x plus y term. So there will be a single line only. But if we just try to make our neural network of more, like if we add more layers to it, like another layer and then another layer. So our model will basically the lines will become more complex. Like it might become like this, and if you add more layers and neurons to it, so it will just like to like become more complex. So basically, adding more number of neurons basically means that we will be adding more complexity to our model. So basically, so the classification line, which is the line which is classifying, will become more complex. So it will try to learn each pattern basically. So if I just make a final line, if our model is very too big, and too complex with many hidden layers and each hidden layer having a lot of number of neurons, then I can basically say that if I just make a final classification line of blue color, so if we have a model with very large number of hidden layers, suppose 10 hidden layers with each hidden layers having like hundreds of neurons, then the model will capture more complexity, more curves of data. So basically it will capture like this. So is this the perfect line for it? Like suppose if I just make the same, basically if I just make the same line, like if the line is like, if I just try to copy the line, it goes like this and it goes like this and it goes like this. So this is basically our classification line. And what if we are testing now? This is the training data set points, this, and all these. And suppose that we have a testing data set point. So suppose it came here, it came here. So is it classifying correctly? the testing dataset points. No, it is not classifying correctly because it is just learning the basically learning the training data too much. It just had learned the training data and it is not doing any good to us. So basically, this is why overfitting takes place, and the major cause of overfitting is neural, basically complexity of our neural network. So let's just suppose that we just make it like I try to explain once more the whole setup. So let's just suppose there is a single neural network, and there each data point is passing one by one from it. So let's just suppose we are having each data point to pass once and then weight updation will take place. So let's just suppose this thing has passed, this data point has passed, and then we basically draw a line. Or basically, if we just try to make that all of the data is passing once. So suppose that we are applying a batch gradient descent and all the data passed with the weight 1, weight W, and WX plus B is the term. So for a single neural node or neuron, a single line just came. But if we are having a complex neural network with many lines, so the complexity of our neural network will increase. Like for two neural network, then there will be two line adjusting like this. But and three neural networks, so it will be like this. So basically, when the complexities are increased, the curves are formed, and our model is trying to learn the training data hard, it is learning it too hard. So when it is learning it too hard, then there is no scope of getting the reasoning out of it. So that's why so that's why it's overfitting with the training data and it is badly performing with testing or validation data. So that's why we should basically try to decrease the neural networks. So that's why we apply different regularization techniques. The basic gist behind the applying regularization technique is that we have to decrease the complexity of our neural network, which is already too much complex if we apply a lot of hidden layers and basically if a number of neurons and hidden layers are increased, we are increasing the complexity of our neural network. So at the end, what is our key goal here? To apply regularization techniques to basically reduce the complexity of our neural network. So that's why what we are doing here is that we are applying the complexity of our neural network by applying different techniques, which we call as regularization techniques. So I hope you got the gist which I just tried to show you. The same thing is basically here that we are applying batch gradient descent and whole of the batch of data is passing and then it is multiplying by it and some linear line is getting. We are basically getting a linear line, and if we increase the complexity like from one neural node to multiple neural nodes in a single layer, then the curve we will getting a more like spiky lines maybe. And if we increase the number of hidden layers and the neural nodes, so it will be like a curve adjusting, like this curve line adjusting. So this underfitting, we can say the neural network is not so much. We are not giving more neural nodes or hidden layers for our data to perfectly get a balanced data. So this is like a curve, but it is like a balanced curve. And this is an overfitting curve because we have increased the number of neural nodes and hidden layers. So it is trying to learn the complex pattern instead of trying to fit into that basically the classification or regression setup. So I hope I made you clear about it. More we will be looking when we will be looking at the codes of hand-on neural network. I hope I make you understand. We'll just go through the code on our date and lecture. So let's just read what is introduction to regularization. In deep learning, regularization refers to techniques used to prevent overfitting by penalizing the complexity of the model. The goal is to encourage the model to learn generalized patterns from the data rather than memorizing the training data. Overfitting occurs when the model learns only the underlying patterns in the data, but also the noise and outliers. Regularization helps by either constraining the model's complexity or artificially increasing the training data set through data augmentation. So basically, if we are getting an overfit, so what measures we can take to avoid overfitting? So like different measures if we can which we can take to avoid overfitting. So to avoid overfitting, we can just try to apply. You can just write, or I will just try to get typed it in notes. So you can just apply training on more data, basically more data, or try to apply data augmentation. This you must be knowing what is data augmentation, and you can just try to apply like to avoid overfitting. You can just apply different regularization techniques. So these are the measures which you can take basically. So, so the same thing is basically written here that through training data set to basically we can increase data set through data administration. So common regularization technique, regularization. Dropout is one of the most widely used regularization techniques in deep learning. It prevents overfitting by randomly dropping out or deactivating a subset of neuron during each training iteration. This forces the network to learn more robust features as it cannot rely on the presence of specific neuron. So basically, the concept of dropout is that if there is a neural network like this, and then we have a input layer and this, and then this. If I just try to make it, so this is our basically the neural network, and what happens is that we apply dropout. So these are our input feature. This is our first hidden layer, the second hidden layer, the third layer, and then the output layer. Suppose it is a regression problem. So basically, what we are doing is that we are applying a dropout. Basically, like if we apply dropout to this hidden layer. So basically, if I apply the dropout ratio to be like 0.5, so what will happen that half of the layer will just these thing will just basically the weights of these will just vanish for that epoch. Like in the next epoch, what will happen that suppose this will go off and this will go off and these two will be working, and then next epoch what will happen, suppose this will go and then this will be working fine and then this will go. So basically the p can be basically the dropout ratio can be applied for each layer. Suppose if I just try to apply 0.25 for this layer. So suppose in one epoch this will go and all other three are working, and for suppose this all other two are all other three are working, but this will go for another epoch, and the same will happen. So what is basically having is that when we apply regularization technique, so we already know because of the complexity of our neural network, the model of overfits. So basically, what we are doing is that for any set of for a epoch, any set of neural networks will become zero. So what will happen that if this is zero and this is zero, so the lines coming out will basically they are useless because when they will multiplied by with the weights, they become zero. So what will happen is that 1 second, please. What is happening? Just so yeah. So if I suppose this these two are zero, so they are not 1 second, please. Um, yeah. So basically, the lines coming out from the layers which are not crossed will only matter, and the other layer things will not matter. Basically, they are not contributing to our neural network. So yeah, this is the diagram. Like if I just copy it also, copy image, and then just try to paste it here. So basically, you can see that this is our standard neural network. So suppose that here are the input layer and the input data are coming. So we applied basically a dropout of like we are using only basically we are applying a dropout ratio of 40% because our out of our five neural nodes only 20 are active, only three are active and two are not active because dropout is applied. So the weights coming out of these layers only matters which are not coming in that which are not being crossed using dropout ratio. And this is happening with every like for next epoch, maybe this is out and this is working and this is working and this is out and only this is. So basically, for every epoch, it will change. The permutations will change accordingly. And the thing with dropout is that in dropout, we only in dropout only we basically on training only these weights are cancelled with a permutation which is handled by the different Python frameworks like PyTorch and TensorFlow. It is basically handled in the back end only. We don't have to like apply that for this node dropout will work for this node for this epoch the dropout will work for this particular node. No, it will be handled at the back end by different Python frameworks and so this is basically our training setup. Like training data will pass for this, and for next epoch, maybe this is out and this is working, and this is out, this is working, and this is working. So it will be handled. But in testing data, there will be same neural network and the weights which have been learned. So what will happen like if we have applied basically if we have applied dropout of like 40% 0.4 because out of the five two are out. So what will happen that the weights we are taking of this all the weights which we are taking from this will be like W1 minus P. Why 1 minus P? Because 60% are basically out of like if you are taking 44, 0.4 is the dropout of here, like 40% of of the nodes of that hidden layers are dropped out. So out of that 40%, 60% of the times they are present. So we are just taking weights multiplied by the probability of their presence, and then like doing like the all other thing like the. So basically, we are just taking the new weight as W into one minus two for testing. We are not dropping out the layers in testing phase. We are dropping out only in training phase. So this you have to keep in mind. So why basically it works? So basically, what happens like I already told that why overfitting happens. The overfitting happens because we have already made our too complex uh, neural networks. So basically, what we are doing that to reduce the complexity, we have to try to reduce the weights. Basically, we have to try to eliminate uh, the neural nodes from the hidden layer. So how we can do it? We can do it by just trying to make them zero. So if their weights are zero, that neural node is of no use basically. So that is why we are just trying to use the permutation and trying to make that nodes to come towards zero value, or we are just trying to decrease the weight of that node by multiplying it through some probability or through some 1 minus p that dropout ratio to decrease the power of that weight. If we increase the weight value, then our model will become more complex. Like suppose that if we are having a hidden layer of 10 nodes and just their weights are also very like very great values or very good and big values of weight. So when we apply dropout, somehow the value of that weight has decreased. So when the weights of values have decreased, then we are just trying to hold up that hidden layer which was giving more complex output. Now because of the decrease in the weights, they will be giving lesser complex output. So our model will this time not try to overfit. So basically, these are the small techniques which we can imply to reduce overfitting. So this was the whole concept behind dropout regularization, and we'll be looking at dropout applications in that. Again, I told that this will be a purely purely a lecture of theory, and we'll be looking at the code in lecture 10. So basically, if we just go through the definition, the dropout is one of the most widely used regularization techniques in deep learning. It prevents overfitting by randomly dropping out or deactivating a subset of neurons during each training iteration. This forces the network to learn more robust features as it cannot rely on presence of specific neurons. So during training for each iteration, a random subset of neurons in node with a probability p, typically p. So this p is basically the dropout ratio. The network thus learns to rely on multiple neurons to make decisions rather than a specific subset, reducing co-adaptation. At test time, dropout is turned off during testing, but the weights are scaled down to account for the missing neurons during training. So the scale down thing I already told you here. So that this thing is only the scale down thing. We are taking the whole neural network in testing time, but we just scale down the weights during testing time. So this is basically the thing like five out of five, like five neurons in a hidden layer. So we just dropped two of it, and this will basically prevents overfitting and encourage sparse representation that some of the weights are becoming or close to becoming to zero. So this is how our dropout thing works. And then we have L1 and L2 regularization. I hope you already covered in data science. So we'll be having a quick revision of L1 and L2 regularization. So another popular technique is adding a penalty term to the loss function that discourages large weights in the network, effectively controlling the model's complexity. There are two primary loss of forms of weight regularization: L1 regularization, or L1 regularization is also called lasso regularization. So this is the value of L1 regularization. Wi is basically the weights, and in L1 regularization adds the absolute value of the weights to the loss function. This encourages sparse weights, meaning that some of the weights will be driven to zero, effectively eliminating certain features and making the model simpler. So there are two types of basically. Actually, there we can say that there are three types. So L1 regularization. Basically, we have many types, but we focus on L1, L2, and L1 plus L2 regularization, which are held together, L1 plus L2. And we'll be basically looking at L2 regularization because most of the time we will be applying L2 regularization only. So, what happens when we apply regularization is that our weights tend to go to zero. So, basically, that is already that you already know that we want our weights to go to or come close to zero so that our model complexity decreases, which in turn decreases the overfitting thing which is happening. So, basically, we are applying L2 regularization or L1 regularization or L1 plus L2 regularization. So in L2 regularization adds a squared value of the weights to the loss functions. This discourages the weight from becoming too large, but doesn't necessarily drive them to zero. So what happens when we apply L1 regularization? That the thing here written doesn't necessarily drive them to zero. And what happens in regularization, L1 regularization, that it will be driven to zero. So it can be like the interview question type of thing that in the last regularization, the weights tend to become zero, which leads to sparse representation, or our model effectively becomes like our model basically becomes like sparse model, so where many of the weights are zero. But in L2 regularization, what happens that our model weights don't the value of that weights becomes very low, but they tend to zero, but they are not zero thing. So basically, this is the difference between L2 regularization and L1 regularization. And mathematical formula of L2 regularization term is this. So this is the penalty term, if I say. So this is the basically the penalty term. The penalty term is added. So this is our basically the loss function. J we can say J is basically L, our loss function. The basic representation which we consider. I hope you will just read it is written. Consider loss function JW without regularization. So this is our because of without regularization, and this is with L2 regularization, a new loss function. So this is our new loss function with the L2 regularization. So what will happen if we just try to differentiate this, and what if I consider this as L dash and this whole thing as uh, cost function or loss function if in case we are considering only the loss of a in a single data point so L and this is our penalty term which we consider as penalty term, regularization term. So what will happen if we just try to differentiate this? So if we try to differentiate this then with respect to W, so suppose W naught basically. So DL naught by W naught. uh, So the rest of the other weight terms will basically turn out to be zero, and you already know the differentiation how differentiation works, and if you just try to update it the updation rule, you already know that W new basically is W naught minus eta WL naught basically the loss total loss differentiated with that weight, so it will be so 1 minus 2 lambda W naught minus theta theta. So basically, this is our final term. I think there is something which I feel is missing. Hmm. Uh, I will check it once, but the core idea, the formula, I will check it once, but the core idea or the thing behind is that this is our thing which is happening. Maybe I am missing something here, the correct formula, which I think lambda by 2 it is, and when it is multiplied with 2, so basically it will be 1 minus lambda, which I will check and tell you. And I just don't want to waste our time on this thing. But the key idea is that this is happening in weight adaptation, and you can see that this whole term, either 1 minus lambda or 1 minus 2 lambda, is called a weight beta term, which we give as a parameter. So this leads to the value basically going to a smaller value. So this is the behind the scene what is happening in L2 regularization is that our weight updation has changed a little by some factor, and the lambda value is basically reducing the weight thing W naught more drastically because the value total value has increased here. Earlier, what was happening, Wn is equal to W naught minus n dl by W naught, but now you can see that there is another term which will be leading to weight value getting more decreasing more drastically, which leads to regularization, which will reduce overfitting. So I will just check it once by what is there any error in the formula? But the idea is that in what we do is basically in loss function we give a penalty term, which is our regularization term, which we also called as penalty term. And because of adding this penalty term with which is multiple, basically having a parameter lambda, what happens is that our weight values tends to basically it becomes very small, which in which helps us in reducing the overfitting. So this is the core idea. Rest everything will be handled at the back end by our different Python frameworks like PyTorch or TensorFlow. So this is basically the key idea which you need to understand. You don't need to go too deep in the into the mathematics. You just understood what is happening and how it is. The formulas are working and how it is decreasing the weights. So L1 tends to produce fast models with many weights reduced to zero, which I already told. Because many weights are turned to zero, the model becomes sparse model. And L2 tends to reproduce small weights, but usually no zero weights. So this was already told, and this is basically the code which will be shown to you later. So you can also see like the regularization L2 which we applied, and this is uh, weight decay thing. I think this is weight decay. We will be using PyTorch for this. So I will try to basically make you understand TensorFlow code also. But I will primarily focus on basically uh, PyTorch framework and not TensorFlow basically. So, but you don't have to worry about the framework. Basically, the key idea concepts will be same. I will try to give you the codes for TensorFlow also, so you can just select any one of them and try to learn from any one of them, and it will be helpful. So if you just try to read the same thing is written, it will reduce overfitting by preventing large weight values and will increase fast models, while to increase smooth models. Techniques to avoid overfitting, this I already told you that we can just increase the number of data and apply data augmentation. So overfitting occurs when a model learns to perform well on trained data but fails to generalize to unseen data beyond regularization. Several techniques to help mitigate overfitting in detail. So what's happening at data augmentation? So suppose if we are dealing with CNN problems, so what we can do? Like if we have a photo of a cup, or a photo of a cup lying on a table, so what we can do? Like to if we have not that so much of data, so what we can do? How we can increase the data? So we can just do some data augmentation or try to basically rotate it or flip it or scale it or crop it. So these are the things which by doing it we can basically increase the number of data points. So like translation is also shifting the mist slightly in different directions. So basically these are the things which we can do to increase the number of data which we call as data augmentation. So data augmentation helps model generalize better to see unseen data. It effectively increases the weight of the training data set with collecting more data. So this is basically the thing behind data. Data augmentation, these things you have already covered in if you have studied ML, so it's no time to put in it. Early stopping is basically early stopping is like when our model starts to overfit, we apply early stopping. Early stopping, I will show you by code. And learning rate schedulers and regularization, these are basically this I will try to show it by code only. What is cross validation? Like what happens if I try to explain you by example, like if you have a data set of 50 data points and we consider uh, basically if we consider to take training data set as we split the data like 50 data set points are split in 80% and 20%, and 80% of the data is used for like training purposes, and 20% data set is used for validation purposes. So what will happen, like if we take some data, take out some random data points, like in first cross validation technique, like if we consider five cross validation technique, like we took 20% of the data, and those data set is the data set which we have 80% data set is are used for training, and the other 20% data set is used for testing purposes. So we got a weight of that. So suppose if we make a clear demarcation like 1 to 40, although it will be happening randomly, but if for example we take 1 to 40 data set points as training and then 41 to 50 data set points for validation. So when we are trained from 1 to 40, there will be some weight, and then we will be using that waits for testing. And then again, in the next validation, we will be taking 1 to 30, and then 41 to 50 as our training data set, and 31 to basically 40 as our validation data set. And for training, for from 1 to 30, and then 1 to 30, and then 41 to 50, we get some particular weight, and then we'll be testing from that weight 31 to 40. And then they will be doing this for like 5 times. The same pattern will goes on. Then we'll be compared the different weights. So we'll just try to out what average out the validation results. So cross-validation involves splitting the training data into multiple subsets. The model is trained on different subsets, and the performance is averaged out. So this I already told that the testing accuracy will be basically averaged out over these force to evaluate the model's generalizability. K-fold cross-validation, the dataset is split into K subsets and the model is trained K times, each time using a different subset for validation and the remaining data for training. The same idea which I already gave you. So this is basically the cross-validation, and all these learning rate schedule and learning rate decay will be looking at the code only, and then with the early stopping, and it will all be made clear in that date and lecture with the code. So I hope this I lecture I already wanted to basically not to cover more on code and just try to give you some simpler idea. This lecture was short because already we did a big lecture, so this lecture is short. And but the upcoming data lecture will be whole revolving around code, and we'll be understanding by code, and we'll be looking different uh, uh, basically different analysis we'll be doing. Like I already had searched for a data set which we can use to train our model, and then we'll be applying different techniques, and we'll be looking at the changes in accuracy when applying these techniques. So I hope I made everything clear about it, and let's just wait for data lecture, and everything will be more clear. Thank you.